taste of the work we have done at the Larnaca Desalination Plant in Cyprus. The objectives are clear. This is the seawater desalination plant producing drinking water using a reverse osmosis process, trying to use the most efficient systems and complying to both water quality and quantity requirements. The Larnaca plant has a quite innovative setup. It's an older plant. It has been operating since 2001, but it has some innovative designs for that time. For example, they were the first to use 8 membranes in the pressure vessels. They were the first to adopt the split first pass system. For the rest of the pretreatment, they use a traditional acidification of the seawater followed by phase separation and multimedia filtration. And just a quick word on boron. I don't want to go into detail on this. I know there's a lot of debate going on around the boron issue. Fact is that there are a lot of plants in the world still facing low boron requirements in their produced water. And boron, as we know, or boron membrane rejection is a function of the amount of boron you have in the seawater temperature and the feedwater temperature. Specifically for the Larnaca Desalination Plant, which is located, as I said, in Cyprus, using Mediterranean seawater with a typical value for boron of about 5 ppm, and their contractual obligation was to produce drinking water with a boron value of below 1 ppm. We analyzed for several years the seawater temperature, at least the intake water of the Larnaca Desalination Plant, and you see this very nice trend where the temperature during the winter time goes to about 15 degrees and then gradually over the summer period increases to 29, even 30 degrees in some cases. Now, as we said, boron rejection is not only a function of the temperature, it's also a function of what form of boron you have in your water, and this is pH dependent. So at low pH you have the boric acid, which is uncharged and which is also badly rejected by the current membranes. But if you increase the pH to, and the pKa is 9.15 here, and then you have the majority of your boron as the negatively charged borate, which is much better rejected by the current membrane. So this is one of the things you can do to increase boron rejection, is to increase the pH. So how are we going to improve boron rejection or boron removal? Of course, we have a couple of parameters which we cannot control. Seawater temperature is not really in our own hands. Neither is the boron composition of the seawater. So we're just going to monitor these and try to adapt our plant to these factors. What we have in our own hands is the design of our plant. We can look for more innovative designs of our plant or more innovative ways to run our plant to increase the membrane boron removal. But of course, as we said, we can play with the pH of the feed water. So in the design setup of the Larnaca plant, they were, as I said, one of the first to implement the split first pass. In this setup, where they acidified the water to a pH of 6.87, at least below 7, they could use the front-end good water quality, about 80% as direct water, as produced water, and about 20% of the back-end permeate had to go via a second pass for further purification. Now, what we done at the Larnaca plant was stop the sulfuric acid injection of the feed water, and in addition increase the pH of the second pass feed water by adding NaOH to the pH of about 10.2. Now, one of the first challenges that this brings is the phase separation process. The optimum pH for your ferrichloride flocculation is around 7. It depends from plant to plant and about it. But here in this case, this was one of the concerns. We still have enough of a good enough phase separation. So we had an extensive trial here to run the pre-treatment at seawater pH 8.2, 8.3. and we proved that this was very much workable. That the phase separation process was still good enough. It was not as good as at lower pH, but it was still good enough to run at the RO plant. So in this new constellation where we stopped acidifying the seawater and we started, or at least for a part of the year, increasing the pH of the second pass, for 6 months of the year, this specific plant did not need the second pass. So you can imagine the huge cost saving this plant had by not using for 6 months of the year their second pass. No use of their booster pumps here, no chemicals here, membranes were not used, so membrane life was extended here. And on top of that, because the 20% that they normally would send over the second pass, which again they would lose apart from it, in total they had 8% more water that they produced. So huge cost saving. Now, by doing so, we of course induced a couple of problems. First of all, we were running at higher pH of the first pass, so we risk here of precipitating predominantly calcium carbonate. If you look at seawater, the dominant scale type that you can have is calcium carbonate. Similar on the second pass, where you go to a pH of above 9, and in this case it was more like 10.2, calcium carbonate precipitation is possible, but equally important is magnesium hydroxide, which is very often overlooked in the second pass. Okay, other problems, some problems that are affecting the plants, of course, the seasonal variation, temperature predominantly, also the plant is operated certain parts of the year, it's peak water demand in summer, for example, so these are all parameters that need to be taken into account, which we have taken into account. Now what are we going to do? Of course we're going to check whether it's really necessary to use an antiscalant, and for that we calculate the saturation indices of the different waters we have here. How do we do that? For the first pass, as I said, we are at pH 8.2. The main issue is calcium carbonate, and for that I think everybody will agree that the Stitt-Davies saturation index is a very nice index to simulate what is happening in terms of calcium carbonate precipitation. It's different for the second pass. Here in the second pass you are in lowly mineralized water at very high pH, which does not really qualify. You're outside of the window for SDSI or LSI calculations, so we need to come up with something different, and that different we have decided that we use the CCPP, which is the calcium carbonate precipitation potential, which is better adapted for lowly mineralized high pH second pass feed waters. That's for calcium carbonate. For magnesium hydroxide, there is not really a good index to predict what is going to happen, so there we took a more laboratory simulation approach to see what is happening with magnesium hydroxide in function of pH and temperature. So as the SI, this is clear at pH of 8.2, we were somewhere between 0.9 and 1.3, which clearly indicates the use of the requirement of an antiscalant. For magnesium hydroxide, we did a trial in our labs at 30 degrees, and here you have the magnesium concentration in function of the pH, and you see that you get a dramatic decrease in solubility of your magnesium hydroxide, even with a small increase in your pH. So normally you are here in the, let's say, above 10 to 10.2. This is more or less the region that you aim for in your as a pH for your second pass. So you see that you can already lose about 50% of your solubility on magnesium hydroxide, which is very important and needs to be taken into consideration when you decide what antiscalant you are going to use. Okay, some pictures here. You have a nice flaky calcium carbonate crystals, which are hard to remove when you have them on your tail elements, and you have the magnesium hydroxide, which are like these pin-like crystals. So it was clear that an antiscalant was needed, and as we are with Dequest and Italmatch, a phosphonate manufacturer, it is logic that we were going to look into our own range of products on what could now inhibit this scale, and our selection was to use Dequest SPE 0111 as a very performant calcium carbonate magnesium hydroxide scale inhibitor. Just a couple of numbers. SDSIs with 2.6 are absolutely not a problem, and we found out that we could easily double the solubility of magnesium hydroxide. We did a trial of about one year, where we used the highest dose rate. So the dose rate is always in function of the temperature, so we used the dose rate at 30 degrees. We ran that for 1 year. We monitored all the operational parameters of the plant, differential pressures, flow fluxes, normalized everything. Compared this to historical data. The plant was already running for several years under the more traditional way, I would say. We compared these data with each other. We analyzed our product, difference between the feed and the brine. Are we not losing any of our phosphonate? Because this is also a potential risk. And afterwards we carried out some membrane autopsies to see what was actually happening on the surface of these membranes. And the result was actually extremely good. After 1 year, there was absolutely no evidence on scaling, not on the first pass, not on the second pass. And this plant is running, well, now it's stopped. Just quick word on the dose rate. Here you see the dose rate in function of the temperature, in function of the SDSI. As I said, we were 0.9 to 1.3 SDSI. This corresponds to a dose rate at 0.6 ppm to, let's say, roughly 1.1 ppm. So relatively low dose rates. Conclusion, as I said, after 1 year, this plant had absolutely no scale formation on their membranes. The plant met its quality and quantity objectives. It did even better by, for 6 months of the year, not having to use their second pass. And this plant, where we did the trial a couple of years ago, we have been running it for the next 5 years. It's now under complete workover, but we have to run the plant for 5-6 years without any issue at all. So it proves that this is very much. I think most people will say, yes, this is very common knowledge, but at that moment this was not common knowledge. And still there are a lot of people who have questions about, okay, boron removal, what in the second pass, what antiscalant, what is important, magnesium hydroxide, for example. I see a lot of people not really taking this into consideration. I think this presentation is still valid for a couple of key ideas that are still important. Thank you very much.